Yes, so well, thanks very much for to the organizers for the invitation to speak, and also ICTS for hosting this instructional workshop. I think they're doing an excellent job in making it run very smoothly. So I'm enjoying it so far very much, even given the time difference. Okay, so yeah, my duty is to in this mini course is to give talk about Heegner points and focusing on the use, the great use that was made of them by Grosject and especially Coulibaggin, improving very spectacular results towards the BSD conjecture. Okay, so I'll begin by giving a general introduction and motivation for what we're going to see in these upcoming lectures. Okay, so we're going to start off with an elliptic curve over the rationals. As we saw in Anupam's talks, lecture series, for example. Okay, and then we have this discriminant. This is going to be a non-zero integer. Okay, which I'll denote by delta. So these are an elliptic curve over the rationals. And then associated with it, as we all also learn, we have the Hasse-Weil function. Okay, so it's defined by an infinite product over all the primes. Okay, and for the bad primes, we have some degree 2 polynomial in p to the minus s. And then for the bad primes, we get something of degree 0 or 1. Okay, where we already seen this. Okay, so AP is for the good primes is p plus 1 by the number minus the number of points on the reduced curve over FP. And then for the bad primes, this alpha p, depending on the reduction type, the singularities of the elliptic curve mod p, it's either 0, 1, or minus 1. Okay, and Anupam already explained carefully what when are each of these possibilities occurs. Okay, and by the Hasse bound, this infinite product is absolutely convergent for in this right half plane for the real part of S bigger than 3 halves. Okay, but of course, nowadays, after Wiles's work, the modularity, we know that this can be analytically continued to the entire complex plane with a functional equation. Okay, so just to set up the notation that I will be using throughout, let me also remind you of this fact. Okay, so by modularity, okay, work of Wiles and others, there exists a way to new form gamma naught of n. Okay, so n is the conductor of E, such that the Hasse-Weil series of E is the same as the L function attached to this module form. Okay, so in particular, this allows us to make sense of the value of this L function at s equal to 1. So LES as an analytic continuation to the entire complex plane, and with a functional equation. Okay, and the sign appearing here will we will encounter it later. So in my convention, well, I'm just going to write it as minus epsilon. Okay, epsilon will mean will appear naturally in some other instance. Okay, so where for some epsilon plus or minus 1. Okay, and this epsilon arises as the eigenvalue of f under the Atkin-Leonard involution. Okay, so if you call that epsilon, then the sign in the functional equation is the opposite to that. Okay, so in particular, we see that s equal to 1 is the center in this functional equation, and therefore the behavior of L at s equal to 1 is of special interest. Okay, and on the other hand, we have the Mordell-Weil theorem that we have also seen in, I hope I'm back now.
Yeah, we are able to see.
Yes, we can see.
Yes, thank you. Okay, so by Mordell-Weil theorem, yeah, if it happens again, I may need to reboot my device. Whenever it collapses, it gives me, it tells me I might have to reboot my device. Hopefully, this doesn't happen again. Okay, so by the Mordell-Weil theorem, we know that the Mordell-Weil group is finally generated. So abstractly, it's a number of copies of the integers. Okay, so call that number R. Okay, let me use R sub E. Direct sum with the torsion subgroup. Okay, some finite abelian group, and that's for some non-negative integer. R sub B that we usually call the Mordell-Weil rank. Okay, and then there is a statement of the BSD conjecture that we all know. I just recall it here without explaining every term again. Okay, that usually is stated in two parts. Okay, so the first part, which is actually the conjecture itself, is that this R sub P can be found by just computing the order of vanishing at s equal to 1 of the Hasse-Weil series. Okay, so this is the BSD conjecture itself. Okay, and there is a second part that is usually referred to as a refinement, which also predicts the formula for the leading term in the Taylor series around s equal to 1. Okay, so the R derivative at 1 divided by R factorial, and then there is the real period and the regulator that once we divide that, we should get something algebraic. And the conjecture predicts that that should be equal to the order of this Tate-Shafarevich group divided by the order of the torsion square times the product of the Tamagawa factors. Okay, and this second part or refinement is what's usually called the BSD formula. Okay, so again, I don't recall each of these terms. They were already explained in Anupam's lecture series. Okay, so that was a conjecture that was formulated in the 60s, and after some work of Kotz and Wiles and Rubin, some breakthrough results in the 70s and 80s, a major result toward these conjectures was done in the late 80s by Grosject and Coulibaly. Okay, so major result towards BSD from the 1980s. How we're going now. Okay, so yeah, I was saying these measures resolve from which reads as follows. So suppose the order of vanishing of the L series at s equal to 1 is either 0 or 1. Okay, so I'm going to write it like this with R either 0 or 1. Okay, so then the following two hold. One is the Mordell-Weil rank is the same as R. Okay, so BSD holds in this case. Okay, and the second part, okay, so maybe I can write here. Okay, so this is the rank. Okay, the number of copies of Z in the Mordell-Weil group. Okay, and secondly, the Tate-Shafarevich group is finite. And moreover, with an upper bound which is consistent with the BSD formula. Okay, so this formula over here predicts a formula for the order of Shah, and the upper bound that one gets, it's consistent with that. Okay, so with an upper bound. Okay, it's important that when one gets from these methods, it's just an upper bound. Consistent with the BSD formula. Okay, so a couple of remarks about this. The first one is that prior to this work, there is another breakthrough that was BSD, but that was restricted to the case of CM elliptic curves. Okay, so for CM elliptic curves, and in the case R equal to 0, there were earlier major results by Coates-Wiles and Ruby. Okay, but these results, instead of using Heegner points, they were based on a delicate study of elliptic units. Okay, and in fact, for people interested in learning about these results of Coates-Wiles and Ruby in the CM case, I saw that on the conference webpage there were some lectures from Anupam from back in 2016, giving an overview of these works. Okay, and the second remark I want to make is what happened more recently. Okay, so as far as the BSD conjecture goes, okay, the equality between the Mordell-Weil and the analytic rank, the progress is still concentrated in these works of Grosject and Coulibaly. Okay, but there's been in recent years further progress on the exact formula for the size of the Tate-Shafarevich group, and therefore the BSD formula. Okay, so I just mentioned it here because a key ingredient that goes into these more recent results is still a delicate study of Heegner points. Okay, but this is not going to be the focus of these lectures. Okay, so these recent results are from around, well, from this past decade, and they were pioneered by Skinner and Wei-Zhang. Okay, and what these results do is can be summarized in this way. Okay, so suppose now, instead of making a hypothesis on the order of vanishing of the L series, we're going to make a more algebraic type of hypothesis. Okay, so we're going to fix a prime P and look at the P infinity Selmer. Okay, so suppose that this is isomorphic. Okay, so this will be a number of copies of. Okay, so let me say ZP rank of the P infinity Selmer group is equal to R, again with R equal to 0 or 1. Okay, so then these more recent results show that under some hypothesis on the prime P, one gets the following. So first, that now the analytic rank is is R accordingly. And therefore, by the result of Grosject and Kolibagin, BSD follows. Okay, so that's what is now usually referred to as the P converse. Okay, and the second thing one can show is that the order of vanishing, the PI evaluation, so this OR P, the R derivative at 1, divided by the usual constants. Okay, so this ratio is known to be algebraic, actually a positive rational number by Grosject. And what one can show is that the PI evaluation of this rational number matches up with what's predicted by the BSD formula. So one gets this is equal to the quantity in the BSD. Okay, so what we could call the P part of the BSD formula holds. Okay. Okay, so as I said, these more recent results still use Heegner points plus more recent techniques. And probably we'll hear some of these more recent developments in the research conference next year. Okay. Maybe this is a good point to ask if there are any questions, given that there's been all these interruptions. If I can say a bit more about the assumption about the prime P. Yeah, so I think maybe the cases of good reduction are fairly well understood. I think the hypotheses in that cases are fairly minor. The case of multiplicative primes is also fairly well understood. The case that is most mysterious is the case of additive prime P. Okay, so if P squared divides the level, I think that's still fairly mysterious. Okay, but there is a lot of work kind of improving and getting better and better results on this in this direction. Yeah, P can be 2, but I think the results about say this type of results, 1 prime and 2 prime, when P is 2, I think certainly there are some cases known in the CM case. In the non-CM case, I think that's also more mysterious. Yeah, but there are some definite results for P allowing P equal to 2 in the CM case. Okay, any more questions? Okay, so I want to get to essentially the result that we're going to be discussing in this mini course. So in order to place that into in the context of this theorem here, let me now give you a brief overview of how the proof of this theorem goes. Okay, so okay, so let's take, the idea will be to take, so this statement was about elliptic groups over the rationals, but the way the proof is going to go is by working over an auxiliary imaginary quadratic field K. Okay, so let's take K to be Q adjoint square root D for some negative integer D, square free. And so as before, we write E in our preferred Y-stars equation. Okay, and then we look at the so-called quadratic twist of E by this character, by this discriminant. Okay, so I'm going to call it the upper K. Okay, and this is just the elliptic curve defined by this equation. Okay, so these two curves certainly become isomorphic over this K, but typically not over Q. Okay, so we look at this quadratic twist and this L series of E base change to K, which you can take it as a definition, is the product of the Castella series of E and this twist. Okay, so the first step in this theorem is the Grosject formula. Okay, so suppose, as we had in the theorem, that the order of vanishing at s equal to 1 of the L series of E is at most 1. Okay, let me call it now R. It's less than or equal to 1. Okay, so then we can choose this K so that the following holds. Okay, so the following two. So on the one hand, the L series of this product is L base change to K, V base change to K, vanishes to order precisely 1. Okay, so depending on whether the original 1 vanishes to order 1 or 0, so what we're saying is that we can arrange for this one to vanish to order 0 or 1 accordingly at s equal to 1. Okay, so that's something that is ensured by some input from analytic number theory. Okay, and secondly, we have the actual Grosject formula that give us about, tell us about the derivative of this base change L function at s equal to 1. Okay, and what they find is one gets a non-zero constant, which is quite explicit, times the Néron-Tate height of some canonical rational point on E over K, which is going to be a Heegner point. Okay, so where Y sub K is a point of E defined over K, and is a Heegner point. Okay, so this point will be defined later in today's lecture. Okay, but now this formula, since we know that this Néron-Tate height is going to be, the height of a point is going to be 0 precisely when it's torsion, we get the following. Or let me say, let me put like this. So what we find is that combining what we have above, we get that assuming the hypothesis in the theorem of Grosject and Coulibaguin, we get a point of infinite order. Okay, now Coulibaguin's theorem is going to take as input this non-triviality of a Heegner point to deduce the statements we had in the theorem. Okay, so the second step is Coulibaguin's theorem. Okay, so it says the following. So suppose this Heegner point is non-torsion. Then one gets the following. One is that, okay, so this point being non-torsion tells us that the Mordell-Weil rank of E over K is at least 1. Okay, and what Coulibaguin can show is that, in fact, it's equal to 1. And second is the finiteness of the Tate-Shafarevich group over K. And with an order of its size, with given in terms of the index of this Y sub K. Okay, so with the order dividing the index of the Heegner point by the square of the index times some integer whose support is well understood. Okay, so for certain integer divisible only by primes in a certain finite set. Okay, so let me say in an explicit in quotation marks. In an explicit finite set S sub B. Okay, so this exceptional set of primes is going to be the prime 2, and the primes at which the Galois representation, the p-adic Galois representation attached to is doesn't have full image. Okay. All right. So, but now, so as a consequence, okay, once we have this finiteness over K, certainly we get the finiteness of the Tate-Shafarevich group over Q. Okay, so, implies okay, let me say it like this. Okay, so we have already concluded the first part of the theorem that the rank was 1. It remains to see that the rank over Q, sorry, we have concluded that the rank over K is 1. The theorem was saying that the rank over Q is 1, and that the Tate-Shafarevich over Q was also finite. Okay, but clearly, if the 1 over K is finite, so is Tate-Shafarevich group over Q. And since one knows how complex conjugation acts on this Y sub K, okay, and one finds that this is epsilon Y sub K plus a torsion point. Okay, so this Y sub K will again appear multiple times later. This is complex conjugation. Okay, so one finds that this point, this Y sub K, belongs to Q precisely when it should. Okay, so one finds the rank Q is exactly R. Okay, where R is as we have here, the order of vanishing at x equal to 1. Okay, so this is in broad strokes how this theorem of Grosject and Kolyvagin goes. Okay, and this mini course is going to focus on this second step, okay, the part coming contribution by Kolyvagin. Okay, so this mini course is going to be a proof of Kolyvagin theorem. Okay, so the way Kolyvagin is going to argue is prime by prime. Okay, that's how he gets to these exceptional primes, exceptional set of primes, S sub B. Okay, so say if the elliptic curve doesn't have Cm, then by Serre's theory, by Serre's open image theorem, one knows that the mod P representation is going to be surjective for all but many primes phi. Okay, so in this kind of proof of Kolyvagin's theorem, we're going to give the more details in the case of working with one of these primes P, in which we have full image, and we can work modulo P. Okay, and the general argument in Kolyvagin just will, for these exceptional primes in this set S of P, he's going to work modulo higher powers of P. Okay, so I'll repeat that later once we get to the precise statement that we're going to be proving. Okay. So before we start going over the details and the precise definitions of everything, I'd like to give like a picture outlining the different steps that we're going to see as we walk through Kolyvagin's proof. Okay, and before I do that, maybe I can pause for questions if there are any. Oh, okay. Is there a formula for the first derivative without involving auxiliary imaginary quadratic fields? Yeah, for the derivative over Q without involving. Yeah, I can't think of any formula of that sort. At least at s equal to 1. So at other values, at other non-critical values, there might be some formula that's, for example, involving Kato's classes, as in work of Bloch and Bailinson. But for at the central critical value, I don't know of any such formula that one can get without passing through an auxiliary K. Yeah. Okay, so yeah, okay. Okay. Yes, in Kolyvagin's theorem, yk is a Heegner point. Okay, so whenever I write yk, this will always mean the Heegner point. And then, and what are the difficulties about R at least 2? Actually, we already see them here. Okay, so what we are lacking is some way of relating the second derivative of the L function or a higher derivative to some kind of arithmetic. Okay, if you hand me an elliptic curve whose order of vanishing at x equal to 1 is 2 or higher, we just don't know what to relate it, how to relate it to any pieces of arithmetic. So yeah, the difficulties is just that yeah, we are entirely it's it's completely open what happens in ranks 2 or higher. And okay, to provide the second question in Kolyvagin's theorem, yeah, the order of E over K is 1. Yeah, it's still being assumed. It's part of step 1. Okay, so step 1 already gives us this, and by Grosject we get this input that Kolyvagin is going to take. Okay. So okay, so now let me give you this picture. Okay, so we have, I'm going to put, it's going to be like a block picture. Okay, so we have the L function of E on the one hand, and on the other hand, the arithmetic of the elliptical. Okay, and of course, we would like to relate these two. Okay, as predicted by BSC. Now, what we're going to have is the Grosject formula will, well, as we've seen, it relates in favorable cases the special values of the derivative of this L function to some auxiliary K to the height of a Heegner point. Okay, so this part is the Grosject formula. So now, the next thing that now what Kolyvagin is going to do is he's going to exploit the fact that this Heegner point defined over K is actually part of a compatible system of similar points defined over a billion extensions of K. Okay, so in fact, this Heegner point will fit into a larger collection of Heegner points, which will be compatible in a sense that we'll make precise. Okay, so we will have points y sub L in E defined over L for varying a billion extensions L of K. Now, the next thing that Kolyvagin is going to do is going to, once you have these Heegner points, we can take the Kummer images to produce cohomology classes. And that construction produces classes defined over L. But in order to run his arguments, what Kolyvagin is going to do is massage these cohomology classes to produce classes defined still over the ground field K. But now by changing the coefficients. Okay, so he will produce classes mod P, but all defined over K. Okay, so the end result will be some, what I'm going to call a rigid system of cohomology classes that I'll denote C sub n. Okay, this will be Galois cohomology classes defined over K with coefficients in the P torsion of the elliptical. Okay, and this will be for square free n. For square free positive integers n. Okay, so by the way, this notation is slightly different than the one we've seen in previous lectures. Okay, so this is how I'm going to denote. Oops. What, for example, in Shaunak's lectures is denoted like this. Okay, so that I denote by S of P is the P torsion on E. Okay, and the process of going from this to the other, maybe put some more room here. Okay, so this is the process of what we now call Kolyvagin derivatives. Okay, and lastly, it's going to be these cohomology classes that Kolyvagin is going to use in order to get a control on the arithmetic of E. Okay, so here one uses control. Okay, and he will be able to exert this control on the arithmetic of E, provided this system is non-trivial. Okay, and the non-triviality of this system will be guaranteed by this input, this hypothesis of the point being non-torsion. Okay, so this will guarantee that these classes mod P are non-trivial for one finite many P, and he will be able to get his conclusion. Okay, but so as I already stressed, this control is if the system is non-zero. Okay, and this will be guaranteed by this y sub k being P indivisible. Okay, so if the Heegner point y sub k is non-torsion, this condition will hold for all finite many primes P, and one will get this control for those primes P. And there may be some primes P for which this y sub k is divisible, but then what Kolyvagin will do is work modulo higher powers of P. Okay, but the ideas will still be the same. It just becomes a bit more cumbersome to have to keep track of these higher powers of P. Okay, that's why in the arguments we're going to see here, we're going to stick to just working mod P. Okay, and also as a last remark on this feature, as we're going to see, what goes into this control is basically global Tate duality, local Tate duality, and the Chebotarev, a clever use of the Chebotarev density theorem. Okay, so all these we're going to see in the upcoming lectures. Okay, and one interest of this argument of Kolyvagin is that even though it was originally applied to this context of elliptic curves and so on, actually it opened the way to a wide generalization of these sort of arguments that allow then progress on generalizations of PSD to be possible by these ideas and techniques introduced by Kolyvagin. Okay, so we're going to hear probably more about this in Changho's lecture series, but here let me just briefly say that this picture we have on the left actually generalizes. Okay, so suppose now instead of an elliptic curve, we have V, a p-adic representation of say Q. Okay, so we have finite dimensional QP vector space with a continuous linear action of GQ. Okay, so what we usually call a p-adic representation. Okay, so then attached to such objects, we can also define an L function. And we can also try to understand the arithmetic of this representation. Okay, which in this context really means Selmer groups. Okay, so as we're probably going to see in Sudhanshu's lectures, attached to such V, we have Selmer groups, which generalize Mordell-Weil and the Chaparevic group of elliptic curves all together. Okay, and just as VSD, there will be yes. Yeah, this V typically is part of a compatible system of p-adic representations, and to such one can attach an L function. Here. Okay, so there will be again a conjectural link between these two. Okay, and the relevant names here are the Bloch-Kato conjecture and the Wasawa main conjecture. Etc. And again, the way this generalizes is that in favorable circumstances, one can relate the special values of this L function to certain distinguished elements. So say certain distinguished algebraic or motivic elements. Okay, so here I'm rather vague, but the thing to keep in mind would be like rational points on elliptic curves or units in number fields or some elements in algebraic K theory, like cup products of single units, things of that nature. Okay, and the link between these two is what usually goes under the rubric of an explicit reciprocity law. Okay, so then if one is lucky, these distinguished elements actually are part of a larger collection of classes which satisfy appropriate compatibility relations under different norm maps. Okay, so these are what we call an Euler system. Okay, so in good cases, this will be part of an Euler system. Okay, so these will be cohomology classes satisfying analogous non-relations as the ones we're going to see for the Kummer images of Heegner points. Okay, and once one has such an Euler system, one can apply the same type of massaging to these classes to produce another system of classes, which will be now defined over the ground field, which will be very rigid in a certain sense that we're also going to see. Okay, so one can then apply this process of Kolyvagin derivatives to produce one of these rigid systems that are now called Kolyvagin systems. Okay, so this terminology was introduced by Mazur and Rubin almost 20 years ago in a beautiful work where they systematically developed a generalization of these arguments introduced by Kolyvagin. Okay, and then once one has this system, whenever the system is non-trivial, one can again get control on the arithmetic of it. Again, and this control will be possible in good cases where the system is non-trivial. Okay, and this in fact goes back to one of the previous questions, what are the difficulties in higher rank? This is one of the main difficulties that we have these systems in the context of elliptic curves. We have, say, the system of Heegner points. We also have the system of Kato classes, as we're going to see in Chanjo's mini curves. But if the order of vanishing of the L series is 2 or higher, we don't know the non-triviality of the system in a way that will allow us to say something in the direction of BSE. And I think there was a question in the chat. Okay, Chunk already replied. Okay. All right, so okay, so now after this general discussion, we can begin giving the precise definitions and going slowly over the different steps in the proof by Kolibagin, which will be going over these 3 steps by Kolibagin. Yeah, so can you once tell was okay. Yeah, so one of the questions is, what do I mean here by compatible system of Heegner points? So this will be actually, if I hope to get to that by the end of today's lecture. Okay, so we're going to define precisely these Heegner points, and we're going to see what are the non-compatibilities. Okay, any other questions before we start with that? Okay, very good. So next, let's define Heegner points. Okay, so first, a brief review from the theory of complex multiplication. So recall. Okay, so let's take K an imaginary quadratic field. And given a positive integer n, we have this O sub n, which is the order of K of conductor n. Okay, so here O sub K is the ring of integers. Okay, and this is a so-called order of K of conductor. Okay, and then, so this we can be with as a lattice in the complex numbers, and therefore we can form this elliptic curve over C, okay, C modulo this lattice. Okay, so this is going to be an elliptic curve with Cm by this order. Okay, and remember what that means. Okay, so the endomorphism algebra of A, which is just all the alpha that send the lattice to itself. So On. Oh, sorry. We could take On, but here I'm just going to take a lattice. Okay, so all the alphas that take the lattice to itself and their multiplication is isomorphic to On. Okay, so whenever we have an A with this property, then the theory of Cm tells us that the J invariant of A is an algebraic number. It's an algebraic integer, actually. Okay. Okay, so the J invariant of this elliptic curve is just the J invariant of the lattice, if you've seen the definition in terms of lattices. Okay, and moreover, when we adjoin to K this algebraic integer, what we get is the so-called ring class field of K of conductor n. Okay, so this is H sub n, which is my notation for the ring class field of K of conductor n. Okay, so this H sub n is it comes from class field theory. Okay, so is a abelian extension of K, whose Galois group is via the Artin map isomorphic to the Picard group of this order. Okay, so let me call CL. Okay, so this is the Picard group. Okay, which is just a generalization of the class group. Okay, so if ON is just OK, this CL OK would just be the usual class group. Okay, so these HN are larger extensions which all contain the Hilbert class field of K. Okay, but instead of being everywhere and ramified, we allow ramification at the primes dividing this integer n. Okay, and the way this isomorphism goes is via the Artin symbol. Okay, so if we have the class of some ideal, okay, so this is proper ON ideals modulo principal ones. Okay, so the class of one such, okay, so this is okay, so this would be a proper ON ideal. So this will be sent to, I'm going to use this notation, okay, so HNK E, where this is the Frobenius element. Okay, so maybe I can erase this. I'm not going to use this again, so to not cluster too much notation here. Okay, so when we are trying to K this J invariant, we obtain this H sub n, the ring class field of conductor n, which is an abelian extension of K, which by class field theory is the one with Galois group isomorphic to this class group. And yes, we're taking invertible ideals. Okay, so to get a group here, we look at invertible proper ON ideals divided by principal ones. Okay. And moreover, you can add here. If we look at the J invariant of A that we had before, we can, now this is an element that belongs to this field. So we can, this automorphism act on that. And also part of the theory of CM is the value of this translate of J of A. Okay, and what we get is another J invariant, but now for this, the original lattice we had, but multiplied by the inverse of this P. Okay. So all these elliptic curves we CM by ON, there is an action of the class group of the order on this set of isomorphism classes of elliptic curves with CM by ON, and this action is simply transitive. Okay, and that's how one draws this. Well, it's one of the results of the theory of CM. Okay, so this is what we're going to need from the theory of CM. Now let's take E elliptic curve as before. Conductor n. Okay, so then by modularity, there will exist, not only there is a modular form attached to E, but the elliptic curve admits a modular parametrization. Okay, so there exists modular parametrization. That I'll denote by capital Phi. from x naught of n going to E. Okay, and this is a map of algebraic curves over Q. Okay, so the map is defined over Q. Okay, where this x naught of n was already appeared in Anupam's curves. Okay, so this is the model curve. Satisfying the following modular interpretation. Okay, so we can look at its c-valued points with the cusps removed. Okay, so that's usually what we denote by y naught of n. Okay, and this will be in one-to-one correspondence. Well, first, it can be identified with the quotient of the complex upper half plane by the action of gamma naught of n, this congruent subgroup. And this is in one-to-one correspondence with what are sometimes called modular pairs. Well, instead of modular pairs, let me call this isogenies. Okay, between CM elliptic curves. Okay, so C mod lambda. Not between CM elliptic curves, between elliptic curves over the complex numbers. Okay, so things of this form. Okay, and with kernel cyclic of order n. Okay, so the kernel of phi isomorphic to Z mod n. Okay, and all these are taken up to isomorphism. Okay, so that's convenient because now if you want to produce points on E, one way we can do it is first produce an isogeny of elliptic curves over the complex numbers, which is something very easy to write down. And then that will produce a point on this curve, x naught of n, which then by a phi will produce points on E. Okay, and the theory of CM will allow us to produce points that over here will be algebraic, and therefore, since phi preserves algebraicity, we will be getting points on E also defined over algebraic extensions of Q. Okay, so in order to produce the good elements here, we're going to now choose an auxiliary imaginary quadratic field K. Okay, so let's take K to be, as before, Q adjoint root D, imaginary quadratic field. Okay, and I'm always going to assume, for simplicity, that we're going to rule out these two possibilities. Okay, so different from the Gaussian numbers are, and they sometimes call Eisenstein numbers. Okay, so for simplicity. Okay, so this is just to guarantee that the group of units in K is just plus or minus 1. It's not really much more difficult to include these two cases, but it would make it more kind of notationally involved to make it all the statements precise, including this case. Okay, so this imaginary quadratic field will be chosen to satisfy the so-called Heegner hypothesis relative to the conductor n. Okay, so such that satisfying this hypothesis that every prime L dividing n splits in K. Okay, so this is the so-called Heegner hypothesis. Okay, and the implication that this hypothesis has for us is that it implies, in particular, that there exists some integral ideal, an ideal in the ring of integers of K, such that OK mod n is cyclic of order n. Okay, so with this, I can now introduce all the Heegner points that we will be working with. Okay, so definition. Okay, so let's take n any positive integer co-prime to n. Then the Heegner point of conductor n conductor n is, I'm going to denote it by y sub n, and is defined by applying phi to a certain point on the model curve. Okay, so this okay, so where this Zn is going to be the isomorphism class of the following isogeny, cyclic and isogeny between elliptic curves over C. Okay, so we're going to look at C modulo On, okay, this order P Salaris, and then just the natural map, the identity on the complex numbers give rise to an isogeny between Z mod On and C modulo this other lattice. Okay, so this by the theory of Cn, this point Z sub n is going to be a point on X not of n defined over Hn. Okay, the reason being that this elliptic curve has can be defined over such Hn, just as this one, and the isogeny will also be defined over Hn. And now, since phi is defined over Q, it will preserve any algebraicity property we have for this argument. So this is going to be a point on E defined over the same field, H sub n, okay, which is, as before, the ring class field of K of conductor n. And then what was the point y sub k that was appearing in the previous statements? So note the Heegner point y sub k in the statement of Grosject and Kolyvagin's theorem. Is just the trace of the Heegner point of conductor 1 down to K. Okay, so is the norm from H1 to H of y sub 1, okay, where this norm is just the usual norm. Okay, we take the sum over the contract. Okay, so H1, which is the ring class field of conductor 1, or equivalently the Hilbert class field. Okay, in other words, the Hilbert class field. And this trace map is just takes a point and sums over all the conjugates of it. Okay, so these are the points, the Heegner points that we will be working with from now. All right, so I still have 15 minutes left, so now I can state and prove the non-relations that I mentioned before and that I was asked about. Okay, any questions before you do that? Okay, so this is our first proposition. Okay, the norm relations. Okay, so suppose we have one of these n as before, coprime to n, and suppose it's of this form, L times m, with L not dividing m inert in K. Okay, so then, okay, what we can do is we have the point y sub n defined over this h sub n. We can trace it down to h sub n, again, just as we did here, by taking the sum of all the conjugates now by the elements in this Galois group, the Galois group of this extension. Okay, so if we apply this norm map to y sub n, we land in the extension h sub m, where the point of conductor m lives. Okay, and what we get is not quite the point downstairs, but a certain multiple of it, and the multiple is interesting. What we get is a sub l times y sub n. Okay, whereas before, a sub l is l plus 1 minus the number of points of E over the field of L elements. Okay, so let's see the proof of this. Okay, so I'm going to just write down the proof for m equal to 0. There is really no difference for the general case, but the notation becomes slightly simpler. Okay, so we're going to do just the case m equal to 1 for simplicity. Okay, so the key point here is that the modular form attached to E is a TL, it's an eigenvector, and the eigenvalue for the L's Fourier coefficient is precisely this A sub L. Okay, so we have T sub L acting on F sub P, the new form associated with E by modularity, is A sub L times F sub P. Okay, so this will translate into the following equality in terms of the modular parametrization. Okay, so this will imply that for any tau in the upper half plane, okay, so remember we have this parametrization phi on x naught of n, which we can view as evaluate taking arguments in the upper half plane. Okay, so I'm going to use that. I'm going to do that here. Okay, so we get this equality above will translate into the following. Okay, you just use the definition of TL, and what you get is this sum of values is the same as AL phi of tau, and that is true for all tau in the upper half plane. Okay, but to get this point y sub n, what we need to evaluate is a very particular quadratic irrationality in the upper half plane. Okay, and to write that, what we need to do is we can write. What we have to do is write take the z basis for the ring of integers of K. Okay, so okay, and I'm going to use this notation for the lattice spanned by two elements. Okay, so I'm going to use this, this span by bracket theta 1. So after this writing, we can the lattices that appear in this term on the left hand side. Okay, so these lattices, the one is spanned by L times theta 1, and the one spanned by theta plus k, comma L, okay, where k is in this range. Okay, so this define L plus 1 different classes in this kernel. Okay, so certainly they define classes over the class group for disorder, but in fact they land in the kernel of this map to the usual class group, sending A to the extension to OK. Okay. So this fact that we get L plus 1 different classes all in this kernel uses the fact that L is inert in K, and also this simplifying hypothesis that we are ruling out these two discriminants corresponding to Q adjoint I, Q adjoint minus 3. Okay, otherwise this statement needs to be slightly modified. Okay, but this kernel is isomorphic by class field theory to the Galois group of HL over H1. And again, using class field theory, one checks that the Galois group of this extension is actually cyclic of order L plus 1. So this is cyclic of order L plus 1. Okay, so in other words, what we're getting here corresponds to a complete representative for all the elements in this kernel, and therefore all the elements in this Galois group. Okay, and one of these lattices is actually OL. Okay, so we have this. Okay, so these lattices define L plus 1 different classes here, and this Galois group acts simply transitively on them. Okay, by CM theory. Okay, so what we find is that this equation that we have here on the left becomes the following. So what we find is that AL y sub 1 is phi of theta by the definition of this Heegner point y sub 1. Okay, but now we can plug it into this equality we have down on the previous page. Okay, so that's going to be phi L theta plus the sum from k equal to 0 to minus 1. Okay, and as I said, the lattice spanned by L theta and 1 is OL. So the first command we're getting here is precisely the point y sub L. Okay, and by CM theory, all these points that appear in the sum are conjugates of this y sub L. Okay, and we get them without any repetitions because the action is simply transitive. Okay, so this becomes the sum of sigma YL, which is nothing but the norm. Okay, and the only thing one we need to check to give the proof for general M is instead you would begin with a basis for OM here. Okay, but there are no essential changes that need to be made otherwise. Okay, so So this gives us the non-relations, and so what we're going to do next time is study some further properties that these classes satisfy, these Heegner points satisfy. Okay, so there will be what is called a congruent relation, and that will give us that this system of classes that we obtain by taking Kuman images of these Heegner points will be what we call an Euler system. Okay, so next time I'll recall this non-relation that we just proved, and from there see how this system of points will give rise to what we're going to call an Euler system, and then go from there. Okay, so I apologize for all the technical difficulties we encountered at the beginning of the lecture, but I think this is a good point to stop for today's lecture. So thanks for listening.
Thank you, Francesc, for a nice talk. Questions from audience to the speaker? All right, so if there are no more questions, let's thank the speaker again.